Section 11.4, the cross product of two vectors in space. Cross products offer us another way to essentially do vector multiplication. The difference, however, is that when you're doing a cross product, the result is another vector. This is different than doing the dot product, which produces a scalar. Now, when you find the cross product, one very important characteristic is that it's orthogonal or perpendicular to the two vectors that you're doing the cross product of. So visually, you can see that we have a UV right here, making, and of course, would determine a plane. But when you find the cross product between these two vectors, it makes that perpendicular to both vector, right? So as you can see, it's both perpendicular to U and to V. And this can really help in different calculations. Now, in order to find the cross product, you basically set up a 3x3 matrix where the top row are just the I, j, and k, the unit vectors in all three dimensions. The second row are the components of the vector u, and the bottom row are the components of vector v. And by finding the determinant of this matrix gives you the cross product. And again, because the I, j, and k are in that top row, working out the determinant gives you the sum of coefficients of I, j, and k. So again, it's going to yield a vector. Now, a couple of important properties. If you do the cross product between u and v, it's equal to the opposite of switching those two around. So interchanging these rows produces the opposite value, which makes sense because when you look at vectors u and v, the cross product simply needs to be orthogonal to both of them, and that vector, of course, could be going up or down. So obviously, having that negative in front just changes the direction of the cross product. Also, if you take the cross product of a vector itself, it equals 0. Now, geometrically, one other important aspect of it is if you want to calculate the area of a parallelogram that's determined by these two vectors, you basically take the magnitude of the cross product. So if you kind of look at this space in here that's shaded in here, this is a parallelogram who's determined by vector v and vector u. And so if you were to determine the cross product of them and then calculate its magnitude, then that would give you the area of this parallelogram. So for our first example, let's just look at the cross product of u and v, and more importantly, once we find it, we'll demonstrate that it is orthogonal to both u and v. So the first step when making the cross product is to go ahead and set up that 3x3 matrix. So in the top line, we'll do I, j, and k, and then we'll go ahead and put u in the middle. So we have 6, 2, and 1. Those are the components for the three dimensions there. For v, we have 1, 3, and 1. Now, as a reminder, when calculating determinants of 3x3 matrices, you basically copy the first two columns over here on the right side. And what's going to happen is we're going to multiply these three forward diagonals together and add their products. Then we're going to multiply these three backward diagonals and add their products, and then take the sum of the forward three and subtract the sum of the back. So what's going to look like is in our first diagonal, we have I times 2 times 1, so that's going to give us 2I. The second diagonal is j times 1 times 1, so that'll be positive 1j. And then we have k times 6 times 3, so that would give us 18k. Then we go ahead and do the backward one. So in this case, it'll be 2 times 1 and 2, 1, and k, altogether make 2k. And then we have I, 1, and 3, so that's going to give us a positive 3i. And then the last one is going to be 1, 6, and j to give us positive 6j. So we take our first group and subtract our second group. Again, the sum of the products of the forward diagonals minus those at the back. Now, when we put all these together and combine like terms, we have a 2i minus 3i, so that's negative 1i. And then 1j minus 6j would give us negative 5j. And then 18k minus 2k would give us positive 16k. And this right here represents our cross product, right? This right here is the vector that's orthogonal to both these two. And let's go ahead and show why that's true. So if I do u and then do the dot product with the cross product, okay, what's going to happen is we're going to get u, which has a component of 6, and the cross product negative 1. And then we add our j, right? So this would be 2 for u and negative 5 in the cross product. And then we have a 1 for k and u and then a 16. When you multiply all those together, and then add them up, it equals 0, which by definition means they're orthogonal, because whenever the dot product is 0, they're perpendicular. Likewise, if you chose v and do the dot product between that and the cross product here of u and v, okay, that's going to give us the components of v, right, which is going to be 1 times the component here in the cross product, negative 1, and then a 3 times negative 5, and then, of course, a 1 times 16. And again, for the same reason, multiplying them all together and adding them up give us a value of 0, which shows that it's perpendicular or orthogonal to both of our vectors. Now let's look at an example of calculating the area of a parallelogram. So in this case, our parallelogram has vectors u and v as adjacent sides. So if we calculate the cross product between them and then calculate the magnitude, it will give us the area of this parallelogram. So step number 1, we need to find the cross product. So now that we found the cross product, all we have to do for the area is calculate its magnitude. So in this case, the magnitude of our cross product is going to be 2 squared plus 1 squared plus negative 2 squared, and we'll take the square root of it. Now when we do that, we get the square root of 9, or 3 square units. Now for our next example, let's show and find a unit vector that's orthogonal to both u and v. Now in this case, what we have to do essentially is find the cross product that makes the vector orthogonal, but then we'll go one step further and create its unit vector. Now, I'm going to skip the work of doing the actual cross product, but when you set it up and calculate it after doing the determinant of a 3 by 3, it works out to be 60i plus 24j plus 156k. And again, we found that by just doing the normal process of the determinant of a 3 by 3. So the next step, obviously, is we want to look at the magnitude of our cross product. So in this case, it's going to be 60 squared, and adding to 24 squared plus 156 squared. Take the square root of it, and that works out to be the square root of 28,512, which we can go ahead and simplify as 36 square root of 22. Now, because our goal is to create a unit vector, we're going to use that magnitude and, of course, multiply 1 over it as a scalar to the cross product. Because that way we'll have a unit vector, right? It'll be a length of 1, but it'll also be orthogonal to both u and v. So we'll do 1 over 36 radical 22 and multiply that times our cross product. So the 60i plus 24j plus 156k. So the vector that is orthogonal, right, and a unit vector with these two is going to work out to be 5/3 radical 22i plus 2 over 3 radical 22j plus 13 over 3 radical 22k. Now the last thing we want to look at is what's called the triple scalar product. Now this is where you take the dot product of a vector with the cross product of two other vectors. So visually, as you can see, we kind of have this situation going on where there is vectors v and w here determine the plane, and again, as you can see perpendicularly or as orthogonal, this is the cross product. What we're calculating then is the dot product between this cross product and another vector u. Now, there's a couple things you can do with this, but first off, to make the actual calculation, it is another determinant of a 3 by 3 matrix. This time, instead of having I, j, and k in the top row, you have the components of u. So in this case, all the values are going to be numbers. And so when you actually calculate this triple scalar product, it isn't going to be a vector like the cross product, but instead a number. Now, what this number can be geometrically is the volume of what's called a parallelepiped. And that's this geometric figure you can see in dotted lines, which is essentially a three-dimensional figure whose faces are all parallelograms. And it's important to note that when you do make the calculation here of the triple scalar product, there are situations where it may work out to be negative, but when you look at it geometrically as the volume of a parallelepiped, you make it the absolute value. So let's try an example. We're going to use the triple scalar product to find the volume of the parallelepiped with the adjacent edges u, v, and w. Now to do this, we have a couple things. First off, we're going to have to figure out what the triple scalar product is, which means we just have to take these three vectors and set them up in a 3 by 3 matrix and then find its determinant. So this is going to be the dot product of u and the cross product of v and w. But again, to accomplish all that, all we're really going to do is make a determinant with a 3 by 3 where we have 2, 0, 1 in the top row, 3, negative 2 in the middle row, and then negative 1, 5, 2 in this row. Now in this case, as I work it out, it equals negative 10. So what that tells me is the volume of the parallelepiped with these vectors as edges is going to equal the absolute value of our triple scalar product. So in this case, it'll be 10 cubic units.